talk will be based on the recent June 4 with Martin Henk and Linke, both from the University of Magdeburg. And I'm especially grateful to Eva because I'm going to use slides prepared for the talks. Alright, so the central object of this talk is a Knapsack Polytope. So what is that? So suppose you have an integer matrix A, this matrix will satisfy some regularity assumptions, which will describe it later. Suppose also you have an integer vector B, then the Knapsack Polytope associated with A and B is a set of all non-negative vectors x, such that Ax is equal to B. So geometrically, shall I do it? So geometrically, take our form of the real points with non-negative coordinates and intersect the form with the affine subspace defined by the equation of x equal to b. So in this case, the Knapsack Polytope is just a signal. So this is Knapsack Polytope. So the first reality assumption guarantees that the Knapsack Polytope is bounded, so it's indeed a polytope, and not an unbounded polygon, right? The second condition, will guarantee that the affine subspace spanned by the Knapsack Polytope always contains integer points. Okay? So we require that the greatest common divisor of determinants of m by n submatrices of A is equal to 1. Alright, so we are going to associate with the Knapsack Polytope a special set which will be denoted by fs of A, which will consist of all integer vectors B, so is the right hand side of our equation, such that the Knapsack Polytope associated with A and B contains at least S integer points. So very well known in integer programming, general optimization programming, is asking if the Knapsack Polytope contains, say, at least one or at least S integer points. So the set S of A is, roughly speaking, containing all affirmative answers to this question. Say it contains all integer vectors B for which the answer to this problem is yes. Okay? So now we're going to consider an example. So we take n to be equal to 2, n is equal to 4, and s is equal to 1. This 4 points here corresponds to the 4 columns of the matrix A. Okay? So then it's more or less clear that our set, the set of our interest, is always contained in the column generated by this by the column vectors of the matrix A. So if you take, for example, this point, then the picture on the left represents a projection of the Knapsack Polytope and the submatrix of integer points in the space spanned by this polytope. And as you can see, they do not intersect. So this point on the right is not in our set. So take, for example, this point is a knapsack polytope indeed contains integer points. So this point is in our set. So the points of the set fs of A look as shown in this picture. So, for example, we can observe that if our point is reasonably far from the boundary, then the point is in the set. You will see later on that it's always the case. All right. So now we'll focus on an important special case at m equals 1. So this means that our matrix A is just one row vector with integer coordinates, and the first invariant assumption implies that all coordinates are strictly positive. The second invariant assumption implies that the greatest common divisor of the coordinates of the entries of the matrix A is equal to 1. So let's again consider an example. We'll take in this example S equal to 1. And in the expression of the rate, I forgot to mention that the points should be non-negative. Okay. So if we consider the structure of the knapsack polytope for various values of b. B is now just an integer vector. Just an integer, okay? So if b is equal to 1, then the knapsack polytope, this example is just a small segment. The segment doesn't contain an integer point, so this, the number 1 is not in our set. Okay? Take b equal 2. The expression is the same. The segment doesn't contain an integer point, so 2 is not in our set either. For b equal 3, the segment contains integer point, so 3 is in our set. And so on and so on. Starting from some integer, all points will belong to our set, right? The last integer, which is not in the set, in this case, this last integer is 5. It has a special name. This integer is called the Frobenius number, associated with integers 3 and 4. More generally, if you consider the general situation for any S, you can define what is called S Frobenius number associated with vector A as a set of all B, integer B, such that the knapsack polytope, is the maximum of the set of the integers B, such that the knapsack polytope contains less than S integer. Less than S points.
So,
right, so
it is Z1 here, right? Okay.
In the example, S is equal to 1.
I mean, it's written there is the intersection with Zn, but you mean the intersection with Z1?
The
No.
it's
Okay.
so right. So
I understand.
yeah. So here it should be kind of
Yeah,
careful.
sure.
So we are in the special case m equal to 1, but n can be any integer, right? Any positive integer. All right. So what is important from our viewpoint, because we are interested in the structure of the set f s of a, right? Is that the existence of the S Frobenius number implies that all integers greater than the S Frobenius number are in our set. So we can say that our set contains a translated form with Apex the Frobenius number such as all integer points in the interior of this form belong to our set. All right. So now we will consider even more special case when n is equal to 1 and s is also equal to 1. In this case, we deal with just the classical Frobenius number. So, very briefly, what is known about the Frobenius number and about the problem of finding this number, which is called the Frobenius problem. The problem is NP hard. It was proved by Henk and if the dimension n is not fixed. For any fixed dimension, the problem can be solved in polynomial time, and this was proved by Linke in 1992. However, the algorithm of Kahn is very complicated, and to the best of my knowledge, it wasn't implemented. So, from the viewpoint of practical computations, Frobenius problem is still a very hard computational problem. You will can be solved in polynomial time fixed dimension. So, it's in practice still difficult. This is one of the reasons why we are interested in good upper and lower bounds. The Frobenius number or this Frobenius number and more generally. So what is known about the bounds of the Frobenius number? From the very general point, all known upper bounds are in the worst case of quadratic order. So the order shown here on the screen. And moreover, it's known that so it's known already from the works of Aliev and Graham, and also from more recent results. The quadratic order is best possible, it cannot be improved. So to say, in the literature there are very many various upper bounds for Frobenius number, and all of them, so to say, correspond to different normalizations. One can say that one is better than others, and some are better in particular, they put vectors, some are better for others. For arbitrary x, to the best of my knowledge, there are just few upper bounds in the literature, and the most recent one was proved by myself, jointly with Knapsack and Henk in 2012. The one shown here on the screen. So we can bound this Frobenius number to above as a sum of the classical Frobenius number plus this error here. The situation with lower bounds is very different. It turns out that one can find an optimal bound. I believe in 2007 I proved by the group is that a number, the classical Frobenius number, can be bounded from below by this expression on the right. Here, Cn is just a special constant of the geometry of numbers, which is called the absolute homogeneous minimum of an n-1 dimensional sequence. So very recently, jointly with Martin Henk and Linke, we generalized this bound. So we proved that in the general case, a very similar bound holds. You just need to replace the constant Cn by a new general constant associated with the sequence. And I can also show that this bound is open. Alright, so now we are going to the more general case when the number of rows of our matrix is bigger than 1. In this general situation, only the case n equal to n minus 1 and n equal to 1 was investigated in the literature to the best of my knowledge. In this case, the set F1A has a very remarkable structure. So suppose this is the cone generated by the columns of the matrix A. Then one can show that there exists a unique maximal with respect to inclusion cone, translated cone, such that all points in the interior of this cone belong to the set F1A. So we call this cone a feasible cone. So in this special case, when n is equal to n minus 1, the maximal feasible cone is unique. So the set has a very remarkable structure. One can show that the situation this property of the set doesn't hold in the general case. For example, in our example before, it's easy to see that the maximal cone is not unique with respect the maximum with respect to inclusion cone is not unique. So here in the picture you can see two cones which are maximal with respect to inclusion. Right, so in the general case, we know that this maximal cone may be not unique. There might be several of them. So what can we say about the structure of our set? We'll use the following trick. You choose any vector from the interior of the cone. And we will estimate location of a feasible cone along this direction. Meaning that so if this was our vector B, then we will estimate the minimum possible T such that the cone translated by the vector TV contains only points of our set as interior. The situation is completely similar to the classical Frobenius number, right? So in the case of the Frobenius number, we simply translate the cone by the Frobenius number, and then all integer points in the interior of this cone are visible. So we are interested in the area of the quantity GS of A and B. And by definition, it's the minimum of non-negative T such that the all integer points in the interior of the translated cone TV plus cone of A are in our set. Right, so what is the natural choice of this vector B? The vector should be integer, it should belong to the interior of our cone. It's natural to take the sum of the columns as the vector. So, the important special case that we define here is the sum of the columns of the matrix A. schema generically. Okay, the sum of the poles is shown in red, but I'm not sure you can see the picture. But in this case, see that the number gs of a is smaller than 1, yes? So if you multiply the sum of the poles by 4 or 5, then the bond translated by this vector satisfies all feasibility conditions. Right. This number gs of a is called the generalized Frobenius number, and we know several bounds of this number. First, in 2012, we proved with Mark and Henk that the generalized Frobenius number is bounded by a constant, which depends on m and n, times the root of the determinant of a times a transpose. And the degree of this bound is optimal. So to say this bound is optimal up to constant. And as an example of the constant, you can take n minus n times the root of n over 2. So this the bound before applies to the special case s equal to 1. In the general case, jointly with Mark and Henk and Aliev, we proved the upper bound shown here on the screen. This bound improves the constant for s equal 1 and the factor of square root of n. And we also managed to obtain the first ever lower bound for the generalized Frobenius number. So this bound is more complicated. Here in this expression, small and capital M denote the smallest and largest absolute M minus of the matrix A. Alright, so I have 5 minutes left, so let me say a couple of words about the techniques which we use in the proofs. The proofs are based on the Minkowski geometry of numbers. And the main idea is to extend the definition of the covering radius. So we define the S covering radius as the minimum positive mu such that the lattice translates of the set mu times p covers the space s times. Right? So if you pick up any point of space, then you're able to find at least s lattice points such that your point belongs to the set to the sets mu k translated by these points. So we know upper and lower bounds for the S covering radius. So the main idea is just to express the generalized Frobenius number in terms of S covering radius. So it's not difficult to do this. So you just define a special lattice associated with matrix A. So pick up any point from the Knapsack Polytope, and then one can show that the generalized Frobenius number can be related to the covering radius of the Knapsack Polytope translated by the vector T of A and B with respect to the lattice lambda A. So in this talk I will only give a sketch of the proof for upper bound. So I can easily show that generalized Frobenius number can be bounded from bound by the SRA radius of the knapsack polytope with respect to A and the right side vector B, which is the sum of the columns of the matrix A, translated by the O1 vector with respect to the lattice lambda A. Then the isomorphic bound the S-coordinate radius in terms of the standard coordinate radius plus some error term. And then in the group you simply estimate the error term using the results of Weiler about the volume of the sections of the cube. So finally, for the usual standard covering radius, you already know an upper bound. So when you combine all those bounds together, you get the results you need. All right. The proof of the lower bound is much more technical and involved, so I'm going to skip it to stop. So thank you very much for your attention.